Today we're going to learn how you can actually price a discrete look-back call option with stochastic volatility using Monte Carlo methods. We're also going to be looking at how you can use variance reduction techniques to further reduce the standard error around your estimate. So we're going to look at how you can incorporate antithethic variates and then control variates, namely delta, gamma, and vega control variates, to actually reduce the standard error of this Monte Carlo simulation. Now, we may not have an analytical solution for this discrete look-back call option with stochastic volatility, but what we do have an analytical solution for is a continuously monitored look-back call option with constant volatility. We're going to use that analytical solution to then gauge in our Monte Carlo simulation the delta, the gamma, and the vega. We're then going to use linear regression to be able to determine what percentage minimizes the squared error between our discrete look-back call with stochastic volatility to the analytical solution of a continuously monitored constant volatility look-back call option. So without further ado, let's get into it. So first off, path-dependent options with a look-back option. So a look-back option, the options payoff are dependent on extreme, so the maximum or minimum values of the underlying assets over a certain time period. There are two standard look-back options. We've got the fixed strike and the floating strike. Today we're going to be looking at the fixed strike look-back options. And this pays the difference, if positive, between the maximum or the minimum of the set of observations over a given look-back period of the asset price to the strike K at time T. So what does all that mean? Well, essentially for a fixed strike, we've got K, we've got a look-back call option that pays the difference between the maximum price over those monitoring dates that we've observed of the stock price minus K. And if that is positive, then we get that value. Now, similarly for the put, what we've got here is for a fixed strike, we get the difference between the fixed strike and the minimum if positive. So this maximum is just described as the maximum of the stock price at these discrete monitoring times, and then the minimum is just the minimum of the stock price over this path. So we're going to be using the Heston model to actually get this stochastic volatility within our Monte Carlo simulation. So here, remember, we're modeling the square root variance process. So here we've got the underlying SDE under the risk neutral measure, where we've got our deterministic component and our diffusion component. Now the diffusion component, square root variance process that we're modeling here, and we've got our rate of mean reversion, we've got our theta, which is our long run variance, and then we've got sigma, which is the volatility of volatility. So here we've got our relationship between our two Wiener processes. So in other words, the correlation between the variance process and then the stock price. And here, for simplicity, we're going to assume no correlation. Of course, we have assumed correlation before, and we've had to use a Cholesky decomposition within our Monte Carlo simulation. Please go back through some of my previous tutorials on how you can actually do that. So let's look at our initial parameters. Here we've got our initial stock price, our strike price, both 100. Time to maturity is just going to be 1 year. We've got a 6% annual risk-free rate, 20% volatility. We've got a continuous dividend of 3%. Now our Heston parameters, again, we've just made these up, but you could use any kind of machine learning technique on actual observed prices in the markets to be able to derive these. And what we've got is kappa. We've got 5, so the rate of mean reversion. We've got the variance that our initial variance, so that's just our volatility, 20% squared. Our long run is just going to be 20%, and our volatility of volatility, our sigma is going to be 0.02. So let's break down the Monte Carlo simulation step by step. So here we're going to go through for each simulation and then for each time step. Now, our discrete monitoring times are going to be at the end of each week. So in our 1 year period, we're going to have 52 time intervals. So let's assume that they're evenly spaced discrete look back. So here we just have our time, which is just 1 year divided by the 52 weeks. We're going to pre-compute our constants. So we're going to take our yearly constants that we have, and we're going to times it by dt for our kappa. And then we're going to times it by the square root of dt to get our adjusted sigma. So now we've just got some standard placeholders, and these are going to be used just to accrue the sum of CT and the sum of CT squareds. So into our Monte Carlo method, for each simulation, we need to initialize our stock price, our initial variance, and then our max that we've observed. So here we generate one of variables, and remember they're uncorrelated. So we've got one that we're using for the variance process and one that we're using for the asset process. So here we actually step out our variance process and calculate the next variance based on the current variance using all our variables. And then once we have that variance, we can then use that to actually model our asset process. So here we can take our next stock price, which is just equal to the current stock price times by the exponential of this drift term and this diffusion term. Now, once we've actually stepped through one place in time, we're going to look at what the current, our new stock price is, and if it's greater than our already observed max, then we're going to set the max equal to that value. And then we step through for all 52 intervals. Once we've done that, we compute the max of 0 or the payoff between this max minus this strike. And then what we do is we aggregate our CT and then the sum of CT squareds. So then we run through all 1000 simulations, and then we can compute the discounted expectation, and then we can also get our standard error using the sum of CT squared and the sum of CTs. We can see here that we get a call value of $15 with a standard error of about 0.45. Now, computation time was about 0.5. Now, how do we just do the exact same thing but actually speed that up? Well, what we can do is you can use NumPy arrays and vectorize this component. It is important to realize though, we're not going to be able to vectorize the time solution because we need to know what the next variance is in the step before we can actually move forward. So it's still going to be incremented by time. You'll see what I mean in a second. Where we get the gain is that we can create an array for all our simulations for each time step. So we have the same pre-computed constants for the Heston model and then our time. Now we're generating one of variables of size n times m. Here we've got arrays for storing our prices and variance process, and we're just filling in with the initial stock prices and the initial variance. And then we've got our arrays for storing the maximum, and this is just a flat array of m, so 1000 variables. And again, we've just filled with the initial stock price. Now we can just run through each time period. So what we're doing here is we need to calculate the variance first, and then we calculate the log asset prices using that variance for each simulation. So we calculate for each simulation 1000 in time j what our next variance step is, and then we can simulate the log asset prices after we've found out what that variance is at time j. So then we can calculate the deterministic component and then the square root variance process, which of course is needed for determining our stock price in the next period. Once we've done that, we've got 1000 stock prices at that time, and we need to just check across all those 1000 stock prices whether for each one of those scenarios it's exceeded our previously observed ST max. Now, if it has, along that path, exceeded that max, then what we need to do is we're just going to replace only those values where it's exceeded it. So in our first time step, it would just stay as 100 for all the prices that went down, but for the prices that exceeded 100, they would be replaced with whatever that value is. Once we run through all time periods then, 52 time periods, then we can calculate the maximum between all of these observed maximum prices in those 52 week periods minus K if positive. Then we can take the discounted expectation to calculate the option price, and here we get $15.67, so very similar to before, and we get a standard error of 0.44. So exactly the same as before, except we have a significantly reduced computation time. Now let's consider some variance reduction techniques. Let's first look at the antithetic variate. So antithetic variate is just where we have two asset processes. So here we've got two asset processes that are perfectly negatively correlated. So here I just need to initialize two arrays and then two arrays for the max. We have the same variance process that's been calculated previously, but this time here we have our diffusion component whereby the first asset is perfectly negatively correlated to the second asset price. This is kind of like 2 for 1. We're only simulating 1,000 simulations for each of the time steps. However, each time step we're actually getting 2 times the benefit because we're using that variable twice. So now we're going to create that mask, and where the price has respectively increased over the previously observed max, we replace it, and we do the same for both the assets 1 and 2. So once we've done that, then we take the expectation of both of those circumstances. So it's just a half times by the first circumstance, payoff, plus the second. So it's like we have a portfolio of 2 perfectly negatively correlated assets. We then just take the discounted expectation of that payoff of the portfolio, and we can see that we get a call value similar to before of 15.77, but now we have a significantly reduced standard error of 0.19. So now we're going to look at a very similar product which we have an analytical solution for, and this is going to be handy for our control variates. So here we have an analytical solution for continuous observations with constant volatility. So as we've said, there's no analytical solution for the price of a European fixed strike look-back call option with discrete fixings with stochastic volatility under the Heston model. However, there is a simple analytical formula for a continuous fixing fixed strike look-back call with constant volatility, and here is the solution. Now, I've got a link to a paper where we have the solution for this fixed strike look-back call, and you can reference it there. But essentially, I've created a class where we initialize the parameters, and then we can calculate the option price. And I do have a vectorized calculation as well as a non-vectorized solution. So essentially, when you have an analytical solution, of course, you can actually just differentiate these equations with respect to the variable of interest, your sensitivities. However, this takes time, and it can often be easier to actually just implement finite difference methods within your Monte Carlo simulation to be able to calculate your sensitivities. So that's what I've done here. We have finite difference calculations to be able to determine the delta, the gamma, and then the vega. So here, as you can see, we can initialize our instance of the class with our parameters that we've defined, and then we've got our continuous call, lookback option. I can then use the functions that I've defined to pull out the necessary bits of information. So obviously I want the option price here, so that's just option price vectorized. And then here I've got our delta FD, so finite difference, our gamma, and our vega. And here you can see what they are for our actual time period, big T. Okay, so now that we've got that class and we can actually reference that analytical solution and get our sensitivities, how can we actually use that? Well, essentially here I want to remind you that we have our general control variate equation. So here we've got our forward initial price of the option. So this is the premium, this is our payoff, and then this is the discrete hedging that we have in terms of our control variates. Now, our control variates are all calculated individually and are different between delta, gamma, and vega control variates. Now, essentially what we can do is, given data for our particular payoff situation, so we're interested in discrete hedging, so we're interested in the discrete look-back call option with stochastic volatility, we can get the price and the payoffs and relate that to certain control variates of interest. So these are going to be the control variates that we actually determine from our analytical solution of the continuous look-back call option with constant volatility. So we can do that essentially by creating a Monte Carlo simulation with both the control variates from our analytical solution and then our payoffs from our stochastic volatility, and then we can use least squares regression to be able to find out what the parameters are of each of those combinations of the variates that we're going to look at, our delta, gamma, and vega, and then what is best to minimize the squared error. So if that doesn't make sense, that's okay. We're going to run through it here. So here is our calculation of our control variate 1, which is going to be delta. Now here we've got the equation for each of those components, and when it is GBM dynamics, therefore we have the expectation of the next stock price being this. So we're going to code this up for the Black-Scholes model, and we're going to look at what the relationship is between delta and the payoff. So here we can use a Monte Carlo simulation and step through time for 52 time intervals with 1000 simulations. Then we can plot the sum of the control variates over time with respect to the payoff, and here we can see a one-to-one relationship. And the reason it's not crossing zero here is that beta 0, our intercept, is actually reflective of the forward price of our initial premium. So here we're going to be using least squares regression so we can find the true relationship between the control variate, hedging, and payoff. And here we can see that we've got numpy v stack, which is just an array of ones, and then we've got our the sum of control variates over those 52 weeks where we've been doing delta hedging. So then we've got 1000 scenarios, and we can see here that it's a one-to-one relationship or thereabout with our delta hedging with 52 weeks. So if we delta hedge and we accrue all those sums over each week in that simulation, we've got 1000 of them, you end up with this graph here. And we can use least squares regression to find out the coefficient of best fit. Now in the same vein, we're going to do that with a portfolio of delta, gamma, and vega control variates, and we're going to see what that portfolio will be, what the beta values are that minimize the difference between our analytical solution and then our look back with stochastic volatility. So we're going to initialize all our parameters again, our Heston parameters. So now we're going to calculate our fixed strike look back call, so our analytical solution at each time period. We're going to calculate the delta, the gamma, and the vega. We're going to simulate our variance process and our log asset process with respect to that variance. And then at each time step, we'll use these delta, gamma, and vega coefficients to actually accumulate these control variates over time. We're going to sum them up, each respectively. And note they have different equations here because of the methodology of how these control variates actually work within the geometric Brownian motion framework. And then we're going to compare these to our payoff at the end of our stochastic volatility look back option. And remember, that's just the difference between our max and our strike. So once we look at that, we can take our linear least square components and we can see the relationship between our payoff of the stochastic look back call option and then our delta, gamma, and vega. And these are what we're going to use as our control variates going forward to reduce the error. What does that look like? Well, essentially, so in this diagram, you can see the relationship between the delta, the gamma, and the vega-based control variates with respect to the payoff. Now that we have an idea of what they are, we can use them then within our simulation. So now we've got the same time intervals and then 1000 simulations. So now we have some control variate constant terms that have come into this equation, and these are determined just for ease of calculation for our accumulation of these control variates. So first thing we're going to do, for each time step, we're going to compute the hedge sensitivities. So here we've got our call price and we've got our fixed strike look back call. And this is determined from our current stock prices at the current time, and then our volatility here, which is the square root of variance. We then calculate our delta, gamma, vega. We simulate our new variance at time step J. We then simulate our log asset prices at time step J. And then now we accumulate our control variates over each of these time periods. So we calculate our delta-based control variate, our gamma-based control variate, and then our vega-based control variate. We then, of course, check whether our stock price has exceeded our previously observed max for that path. And then if so, we just replace that. We can then see that we get a call value of 16.15 with a standard error of 0.2, and the calculation time has gone up significantly. Now we're going to consider what happens when we have the antithetic and the control variate together. So here we're doing the exact same thing, except we have two asset paths as well. So now we've got two call options with that fixed strike look back call analytical solution. We calculate two delta processes, two gamma processes, two vega processes. We simulate the variance process, one variance process, and then use that to actually simulate the next log asset prices for time step J for both 1 and 2, which are perfectly negatively correlated against each other. We can then accumulate our control variates, and now remember our control variates are actually the sum of both scenarios. So we have like two different portfolios here where we've got our stock price 2 and our stock price 1, and each for 1,000 times. So now that's for our delta, our gamma, and our vega. We then have two masks, which is we're just checking for our stock prices. If it has exceeded our previously observed max, replace it. And then we compute the expectation. And the expectation is, of course, the average between these two scenarios, ST1 and ST2. And because we've accumulated ST1 and ST2 already within our CV 1, 2, and 3, we can just add that in here and divide by 2. So we've got our maximum of ST1 max minus K plus the maximum of 0 and ST2 max minus K plus our beta 1 times CV1 plus beta 2 times CV2 plus beta 3 times CV3. And remember, those are what we calculated out of sample before using linear regression. Here you can see we've got a standard error of 0.1 and we've got our core value of 16. Now, calculation time has almost doubled. We can compare our calculation times between our slow estimate, fast estimate, and then our reduction in standard error compared to the antithetic variate, control variates, and then the combination of antithetic and control variates. Here you can see that we get about a 4.5 times reduction in using the antithetic and control variate compared to just a normal non-variance reduction technique. Now that does come at a 62 times the relative computation time as just a simple Monte Carlo simulation. So as you increase the accuracy of this model by trying to add control variance and reduction techniques, then it's important to remember that there is a trade-off with computation time. Now, the reason the control variates here haven't done nearly as well as in previous products is because the relationship between our stochastic model look back call payoff is not that closely aligned to our continuously monitored look back call option with constant volatility. So here you could come up with a variety of products that might better fit the relationship between the payoff that we're actually trying to model here. So thank you very much for listening. I hope you enjoyed, and until next time, YouTube, see you later.